and the title is Putting Flat Lambda-CDM in the Bin.
Right, yeah, so I'm going to put flat Lambda-CDM in the bin. Yeah, or at least try to do it. This is based on two papers, one that appeared today and one that's from March. And let me start with some motivation. Okay, so the motivation is that we have these cosmological tensions. And there is a biasing in H0 between, say, determinations of the SUMA model, the Lambda-CDM model, or extensions of it, and then local determinations, which are model independent. And it doesn't make a difference which distance indicator you choose. You always seem to find that the local determination is high. And I have a picture of Steven Weinberg, because Steven Weinberg tells students to go look for messes. I think this is a mess, but there is some structure to the mess. And this biasing is sort of helpful in some way. I mean, just to pick up on a comment with Donghui from Donghui's talk earlier, what this tells you is basically you shouldn't be able to change lambda with an effective field theory in the traditional sense, an effective field theory of dark energy, because it would it takes your model and pushes it in that direction. So it pushes further away from the local determinations. It's easy to show that. Now, I'm going to talk a bit about what is matter density, right? This parameter in Lambda-CDM. And there's some funny data set due to Risoliti and Lusso. They've been working on quasars. They've been trying to build a Hubble diagram for quasars since, I think, the early 2010s, maybe 2015, they wrote their first paper. These plots are taken from their Nature Astronomy paper from 2019. And what they have is they're assuming that there's a relation between luminosity in X-ray and luminosity in UV, and it's sort of shown here on the left-hand side here. Now, the luminosities you don't actually observe; they observe the fluxes. So the fact that there is this linear relationship between the log of Lx and the log of LUV is sort of an assumption. At least the slope of it seems pretty robust. Because that comes from the same relationship in fluxes. But there is some sort of intercept here that basically it's not clear if that's a constant or not, or if it evolves with time. But in principle, this data set is something that allows you to go deeper than supernovae. And people have been studying it. I'm interested in it because if you buy this data set, then you can get a sort of 2 sigma statement that the universe is anisotropic. Yeah.
You see the same reason that their argument is
right. Yeah, we've just it is circular.
Yeah.
It's certainly circular because of that constant, this intercept.
Mm-hmm.
I think the slope is robust. There's a huge amount of scatter in the data. So I think what's shown here is basically, in yellow is basically the quasars that they're using for cosmology. And what this stuff here is, or the gray stuff, are quasars that they're basically cutting out, that were in their initial cuts. And the delta is basically a measure of the scatter in the data. So these are messy data sets. And just to put that in perspective, this is the Hubble diagram they have. Okay, so yeah, again, the quasars are essentially in yellow. Huge amount of scatter. This cyan is essentially the JLA supernovae data set. So those have very tight errors. And the red are essentially their binned. So what they've done is they've binned their quasar data. I think the magenta here is the Lambda-CDM model with Planck values, so 0.3. And their best fit is basically the black. So basically what you're finding is, basically in their distance modulus here, it sort of falls under Lambda-CDM at high redshift. So yeah, this is why they got published in Nature Astronomy. There's some nice stuff. Anyway, we were interested in this just to show you that. Actually, let me point out that they use some sort of model independent way of doing this, which is a kind of flawed Taylor expansion. It's a Taylor expansion that they shouldn't have used. So the results are sort of dubious at best. But if you take the flat Lambda-CDM model and fit the data, the same data, you will find that you get a very large value of matter density. So basically, it's almost 1. So if omega m is equal to 1, there's no space for dark energy. So this data set, this quasar data set, it essentially sees a universe without dark energy, more or less. And one thing that I realized earlier this year in some work with, again, we came back to this data set, is that if you restrict that data set to some very low redshift range, like between 0 and 0.7, and you fit it, there's some additional nuisance parameters, and the data sets are slightly different in some way. But the omega, what you can find is basically at least there's a peak around 0.3 for omega m. Okay, so what this is telling you, actually, let me go back to this plot here. What's happening here is the quasar data is being completely guided by type 1a supernovae. So basically, the quasar data is poor quality data, supernovae is good quality data. So they're basically anchoring on. Like your quasars don't, like when you fit that quasar data with the supernovae data, the quasars adopt the best fit of the supernovae. Right? This is not an honest fit. Basically, you're hiding your poor quality quasar data behind your really good quality supernovae, but still at high Z, there's like a deviation. So you start to see a deviation at high Z. But any deviation up to here is just hidden by the supernovae. But if you take the supernovae away, you find that, well, this is what you would get from your full sample. Omega m would be essentially 1. And then at low redshift, you can find that omega m is close to a Planck value. And then what you find is you go out in redshift. So you start from Z equals 0 to 0.7. You go out 0.8, 0.9, 1. You will find that this value of omega m ticks up towards 1. So that was in our March paper. It was quite interesting. The same paper also shows that this thing is there in the Pantheon supernovae data set in a way I'll describe in a bit. Anyway, so today I want to discuss Flatlander Cdm. This is basically Planck's pie chart. It says that the universe is 30% matter. And let me remind you what the Flatlander Cdm model looks like. It's got a Hubble parameter, which just essentially 2 parameters, h0 and omega m. So it's h0 squared, 1 minus omega m plus omega m, 1 plus z cubed. All z dependence is in the 1 plus z cubed part. So I can write it as a plus b, 1 plus z cubed. Now a is basically h0 squared, 1 minus omega m, and b is h0 squared omega m. Now, what I want to tell you is you can prove using analytics and mocks that the probability of you getting this number, omega m equals 0.3, at high redshift, in a high redshift bin is almost 0. That's an intrinsic feature of the Flatlander Cdm model, that you shouldn't be able to, if you basically start binning your bit data and you go to high redshifts, you shouldn't get 0.3, or the chances of getting 0.3 are very, very small. Okay, so let me try and show this to you. So this is some representative DESI forecast data in H of Z. There's 29 data points. And what I'm going to do is just bin them in 4 bins. So I'm going to split it up into 7, 7, 7, and 8. You see the data quality is a little worse in the last bin, so I'm putting in an extra data point. And then I'm going to basically construct a large number of realizations of this same data, just randomly, using input parameters that are, the Planck input parameters, H0 67.36, omega m equals 0.315. And then I'm going to use a constraint omega m h squared, which, what does this constraint do for me? This h is basically h0 divided by 100. So what it does is it tells me what b should be. It's basically a constraint on b, a Gaussian constraint on b. And you can take it away. It doesn't make a difference. Okay, so this is the result of that exercise, which is basically I've got my 4 bins, lowest redshift, next lowest redshift bin, and basically I'm constructing, let's say, 10,000 mock realizations of the data. I'm fitting it back. Now, what you find in the lowest bin, let me just show you first here, is that I have nice Gaussians in, let's say, blue. I've got H0 to be, I guess, whatever the input is, 67. And I've got omega m to be 0.3. So you're getting these nice Gaussians. You get back what you expect. It's a distribution of best fits, basically. And the same thing, we can see the nice Gaussians over here in A and B. But what happens as you go up in redshift? A is essentially your dark energy density. So that term becomes less relevant. And because it's becoming less relevant, its distribution has to spread. So basically what A is doing is A is basically a Gaussian, just keeps expanding. And B is the relevant term. B is basically the distribution in B is becoming better and better and tighter constrained as you go up in redshift, right? So there's sort of like a seesaw thing where basically, B becomes better constrained and A becomes less constrained. But if you use the usual priors or constraints, as you call them on Lambda-CDM, you will eventually hit A equals 0. So your best fits start piling up on A equals 0 in the high bins. And what does that translate into? That translates into omega m equals 1. So in the high redshift bins, you are finding these big, long, non-Gaussian tails that go out to omega m equals 1. And because of B being constrained, if you get tails here, you also get bumps here. So this bump is basically corresponding to omega m equals 1. And this is a generic feature of the Lambda-CDM model. If I had taken any input value, I would find exactly the same thing because lambda is an irrelevant parameter at high Z. Okay, so this is the basic idea. A is basically H0 squared minus B. We know that the distribution in B is contracting. It's becoming better and better constrained. A, we know, has to expand. So the only thing that can expand here is H0. Your distributions of H0 has to expand. And this distribution expands, it expands up to the point that omega m hits 1. And then it can expand in the other direction as far as, so the large values of H0 come down to, they're essentially small values of omega m. Now, what I'm going to show you here is, this is the fourth bin. This is basically the fourth bin of my mocks. And now I'm assuming that the data quality is the same, but I'm displacing it in redshifts of 1. So basically, before this was, it was essentially it was 3.6. Now I'm just shifting that, so it's now between 3.3 and 4.6. Yada 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 yada. So I'm not changing the data quality. So as you do that, what you find is that there's essentially more of your best fits are piled up here, and then this peak is shifting in that direction here. Okay, so your input value, which was 0.3, is going to 0.25 and 0.2, and again, this is completely just mocks. Everything here is under control, and we know what's happening. That it's that spread in A that is basically, it's as you just keep going in this direction, you're going to find that everything's piled in this direction, everything's piled in this direction, and then there's some, sort of uniform probability of getting any value between 0 and 1 in between. Okay, so that's completely generic to the Flatlander Cdm model. What it tells you is basically, if you believe, you can get 0.3, okay, we get 0.3 like from observables in the late universe, let's say below Z equals 1. But if we had data that went up, at some point we would find it, we could find it at 0.3, but it's unlikely. You're far more likely to get a different number, right? Your omega m equals 1 or omega m equals 0. Okay, so the question now is, can you observe this in real data? Can you see this effect in real data? And you can. So if you take type 1a supernovae and start taking away the supernovae at low redshift and just focus on that high redshift bin, you find evolution. So you find that H0, which for the full sample, it's about 70. This starts coming down and omega m starts going up. So basically omega m is increasing with the redshift bin for this real data set. You find the same thing with observational Hubble data, which is basically cosmic chronometer data and baryon acoustic oscillation. So these are direct determinations of H of Z at a given Z. The probability here, I'm basically quantifying using mocks. I can explain it if people are interested later. And you find the same thing in the quasars as well. Now, quasars, let me sort of say that, okay, type 1a supernovae are essentially the gold standard of standardizable candles, right? And BAO, we also have great confidence in. Quasars, we don't know what's going on. But again, we have the same trend where basically at low Z, you find, these values here are just kind of crazy. And essentially they're guided by my prior. If this is very small, this is very large. This thing more or less has to give me a Planck number. But you can see this number here is reasonable. This is what I was telling you. This is almost a Planck value for 0.3, and this H0 number is good. But then as you go further up and further up, this sort of this goes off towards 1. So there's 3 data sets that are doing exactly the same thing in the Flatlander Cdm model. And the only thing is we just don't know if quasars are standardizable candles or not. Okay, so basically this is just to show you that we did the simulations and we can quantify the probabilities. Basically, so this is basically, okay. So what we did is we took not Planck input best fits. Okay, this one here is basically this is observational Hubble data, and you basically fit the whole data set. You get a value that's close to 0.3. It's not exactly the Planck value, but then you use that for mocks in the same redshift range where you find the discrepancy, where basically your parameters have evolved. And so basically our real value was out here, and the omega n equals 1. And what you would guess, or what should be what you would expect to be the number based on the entire data set is basically here. You have these long tails, and this is just outside of 2 sigma, basically. So all I'm saying is that there is evolution. There seems to be evidence for evolution in all of these real samples in the flat lambda CDM model. So just to wrap up, cosmological tensions debate assumes H0 and S8 are constants. People are comparing things in the early and late universe, and they get different results, and they're wondering, why am I getting different results? People are assuming that these are constants, right? That these are unique, they can be uniquely determined. And can now argue that omega m equals 0.3 is unlikely at some z. Like, if you went to z equals 10 and you found you had an observable and you got 0.3, that would be a fluke based on our analysis. There's no reason in the world for you to expect to get 0.3 if you had bin data there, right? And all of this is due to a simple analytic fact that basically A has to be spreading in the Flatlander Cdm model. This is just insensitivity to A. The parameter A is, as you go up in redshift, that's poorly constrained, and so the distribution just has to spread. And so I would expect evolution in redshifts in the Flatlander Cdm model. And remember, what this is doing is the Flatlander Cdm model is a dynamical model. So what you're doing is binning a dynamical model, and you should find that all your fitting parameters have the same value. If they don't have the same value, then that's a bad model. Fitting parameters can't evolve in any sort of dynamical model. So this is, so basically we have a 3 sigma statement that the Flatlander Cdm model is, it's too simple, basically. Similar trends have been observed in strong lensing determinations of H0. And let me just explain where I think this is going. I think Flatlander Cdm is just far too simple. And you still have a H0 problem. You have an S8 problem. As you build up the tensions in different observables, there's one thing that basically people don't like talking about, but it's there regardless. Like, all of these tensions are there within the working assumption that the universe is homogeneous and isotropic at large scales. And now, if that's not true, then H0 is not defined. Poorly defined. H0 only makes sense if FLRW holds. It's an integration constant in the Friedmann equations. So if you put in FLRW, you get H0 for free. But if FLRW doesn't hold, then H0 doesn't have to be a constant. It can be anything. It's just an average. Now, let me just point out some things that are there. There are larger than expected bulk flows that don't converge to lambda CDM expectations at very low Z. These are documented by various groups at this stage. There's still some debate there. We've got some anomalies in galaxy cluster scaling relations that are pointing to, they're picking up anisotropies, and the direction is in the direction of the CMB dipole. This is more or less at Z equals 0.1. There's variations of H0 on the sky in the Hubble, like in the Hubble diagram. So this is some of my work, and this work of, I guess, other people basically as well. There's discrepancies in the cosmic dipole. This is by far the most serious thing now. There's a 5 sigma tension in the cosmic dipole between the CMB and an inference we make of the dipole in the late universe. I can explain it if you're interested. And there's variations of the cosmological parameters in the CMB. So when Planck tells you that they've determined H0 to be 67.4 plus or minus 0.5, if you mask the CMB, if you throw away half the sky, you can get 70. And if you mask the other part of the sky, you can get 64. So there's at least one paper in the literature that shows this. It's published. And what's interesting is that the axis where they find these variations is essentially the axis of, or the dipole of the hemispherical power asymmetry. So these are anomalies that we know are there. They're there in WMAP and Planck. And this is kind of interesting. So this sort of says that you may not be able to do cosmology at the 1% level within FLRW. You may be able to do it at the 10% level. I think this is what that statement is saying. And I just want to point out we've got a review that's appearing soon with some people here at APCTP, I think in the next few weeks or so. But if these anomalies go away, then you can discuss H0 tension. If these anomalies are there, then it makes no sense discussing H0 tension. It's not really, it's a symptom. Okay, so let me finish on that, and I'll take questions if there are any.
Okay, thank you very much. Any question?
Yes, I have a question.
All right, Moon has a question. Yeah, Moon.
Right. So will you show your calculation about H0 by dividing the bins? So
Right. Which one? This one?
no, I mean you showed some real data, bin data. But yeah, here.
This one, right.
Right. So I mean, then what's the behavior of error as you, I mean, increase the bin to higher jet?
What do you mean by error?
Because I mean, you show just the best fit value of H.
I just yeah. So what I'm doing is basically these are the best fit values. So these have an error associated to them, right? But now what I'm doing is okay. So I don't show it, but there's a result for the entire data set, which I think is 70 and 0.3, right? If you use all the data, this is type 1a supernovae.
Right.
So basically what I'm showing you here is the same result where I'm using those values as the inputs for mocks in this range. So basically I'm taking this data, where is it? This data here, right? So there's something like 20 data points or 39 data points. It's something small in this range. And I'm basically mocking up Lambda-CDM many times. And of course I get back my input parameters. So basically I get back 0.3, which is basically for the whole, basically what I'm using for the mock. And then you're finding that this was our real value out here, right? So I'm not actually, these are all just best fits.
Right. So I mean, what I'm worrying is that I mean, as you increase the high jet bin, so what I'm worrying is that I mean, error is also increasing. So
it is, but this is here in the spread. Like so, at least for some of the errors encoded in the mocks, right? It is spread of this distribution. But I mean, there may be an error that's intrinsic to this point that I haven't taken into account.
Okay, so by the way, here H0 and omega m, you mean that the current value, not the evolving value, right?
So what I mean is basically if you take a data set and fit H0 and fit omega m, you get some results. But then you can find some, high redshift bin or subset of that where you may get different results. Now I'm trying to quantify how unlikely is that given the results of the overall sample. And to do that, I'm basically constructing mocks. And then I count the number of mocks where I get a larger value. And that gives me essentially probability.
Right, but what I'm confusing is that the omega m, for example, is defined at Z=0, and H0 also.
No, omega m is a fitting parameter for me. It's H0 and it's omega m. I mean, I'm not interested. Lambda-CDM is a dynamical model.
Right.
Right, and it has fitting parameters H0 and omega m. Cosmologists fit them all the time. So for me, I don't assign any physical interpretation to these guys.
No, actually, that's the parameter defined at Z=0.
Right, but okay, so this is a matter of interpretation, how you want to interpret this. But this to me is something that cosmologists fit to data. This is something that cosmologists fit to data, and I can always bin. It's a consistency check that I can break up my sample into bins and get back the same result. And when you bin data, what you do is you're reducing the statistics, so your errors increase, right? And those errors, Moon, are basically, some of them are in this distribution here, because basically, say I only have 20 data points in that bin. The chances of getting some weird configuration by randomly generating 20 data points, you could easily end up out here, right? That is, we clearly get omega m equals 1. I mean, this is just like 1.7 sigma or so. it's not very significant.
Okay, so because of the time being, so
Just leave
maybe
it.
last question. Can I?
Or we can discuss over coffee then.
Okay.
All right, good.
Okay, then
Because
maybe,
basically we'll discuss over coffee.
then maybe let's finish the session and let's continue during the coffee break. So let's thanks to speaker again. So we will resume at 11 a.m. Thank you.
Can I ask questions, or do you want to talk?
I'm moving